Good morning, and I forgot to do this the last couple of class periods, but today I am remembering it is time to do the Prisoner's Dilemma tournament in front of the class. So I'm going to run this, and we're going to see how your various strategies performed. So without further ado, I will hit run, and here we are. Let's see what came out on top. So in this run, the number one strategy was Pam Gephardt won. Sadly, she is ill today and won't be in class to discuss the nuances of her strategy. Then Paxton's number 5 is number 2. Ivy's number 2 is number 3. Jake's number 3 is number 4. Morgan's 3 scythe, descriptive, evocative.
Yeah, I did that because one, I wasn't going to be able to keep up with what each of them did without doing that.
Yeah, and then Sarah Vogel's number 1 comes in after that, and Uray's number 3 comes in after that. And at that point, we hit kind of an important cutoff, right? So the tit for tat strategy was the historical winner in the tournament. And so from here on up, we have the strategies that were superior to it, that you all created, at least superior in the context of this specific grouping. Going down further, though, is certainly fascinating, and we will. So that's that cutoff. So following closely behind was Tate's number 4 strategy, then Graham's number 4, and then Morgan's randomized strategy. I think I've got a guess as to what that might be like. And then Elijah's number 4, and they sort of go downhill from there. So what I'd like to do now is scroll back up, and we're going to look at these one at a time, the ones that are better than tit for tat. And for those of you that are here, I'll ask you to explain them. For those that are not, we're just going to kind of stare at them and see if we can figure out what the strategy was. So, of course, I am chiefly intrigued by Pam Gephardt 1. So let's see if we can discern what her strategy was. So I'd like to invite you all to look at it, and then somebody see if you can translate this code into a description of her approach.
It's typically, okay, so here's what I see. And this looks similar to a Graham trigger. Because there's no else to say otherwise that change back to false. So it's most likely when it starts defecting, it's going to start defecting with it.
So what do you all think? Did Morgan correctly grasp the content of this strategy? Sounds plausible to me, right? So the very first time the opponent defects, it starts defecting, and it never stops.
Which is very,
no forgiveness.
It's very similar to Graham trigger, which reminds.
So let's look at Paxton 5 next. So Paxton, what was your strategy here?
Start out cooperating, and if your opponent ever defects, defect forever.
It is essentially identical to Pam's, and total score earned is 38,165 for Pam's and 38,140 for Paxton. So they turn out to be exactly the same strategy. And it looks like the only real explanation for the difference is some amount of randomness that crept its way in.
Yeah, which that may have been created from the events of my.
Yeah. Oh, we're going to look at it. So next we have Ivy Monroe 2. This one looks a little bit more complex. So Ivy, why don't you talk about the strategy here?
So mine was also doing the same thing, recuperating and then infecting after they forever.
So let's see. So why did you have the defected once versus defected? What were you going for there?
I was going for like very variable, so after they infected once, it would always infect after. Which I guess I did them.
Oh, I see what you mean. So because these two clauses do exactly the same thing, there's not much to say. It could have been the other two. Okay. So that makes sense. And again, that score is not far behind. So let's look at Jake Norden 3. This is getting a little more complicated. Jake, why don't you talk about Jake Norden 3?
Well, mine was cooperating too, but I used a int instead of another way to do it. So every time if the opponent defective, it would add 1 to I, and then if I was greater than 0, it would
Oh.
return true.
Okay.
And then other than that,
So it sort of boils down to the same idea. All right.
I think okay, and not to be because mine's is relatively simple. The trigger, okay, so the idea was that the trigger was that. So, okay, so the idea was that it was going to have a trigger statement. Once the trigger statement, so that's that else if right here. It was supposed to, once that else if triggers, it will activate the trigger statement.
Trigger goes up to 1, defect is true. Whoops.
And then
From there on out.
it'll run the first one. It was basically I've noticed that I think Grim Trigger is king in this scenario
Okay.
because
So-
there seems to be a lot of Grim Triggers.
All right. And Sarah's number 1, again, is unforgiving. And then Erase number 3. Okay, this looks a little more complex here. Why don't you talk about what this strategy was?
Well, I mean, the part where if the opponent is defecting, then I defect 2 is the same. But for the else statement, I would roll a dice, and if that dice was 1, 3, or 5, then I would also defect. But if it was 0, 2, or 4, then I would not defect. And I think that's what it was.
So if your opponent cooperated, you defected half the time.
Yeah.
So this was on balance pretty successful, but I think it's worth pointing out that the once and done's kind of clustered between 36 and 38,000, and here we had a drop of 4,000 points. Now, interestingly, it wound up putting it within 5 points of tit for tat. So in its own way, in this mix of strategies, this was weirdly equivalent to tit for tat in performance. It does suggest something interesting, which is that the forgiveness aspect of tit for tat maybe doesn't always need to kick in, you know. So pretty fascinating. Okay, let's look at a couple more. So Tate, why don't you talk a little bit about your number 4 strategy?
So it cooperates regardless of how many defects until there's 2 in a row.
Mm-hmm.
And then it defects. And then it plays tit for tat.
Okay, so it is a little friendlier than tit for tat. in terms of performance, it proved fairly comparable in this mix. And Graham, let's look at your number 4. Bless you. Okay, this is getting interesting. So, Graham, why don't you talk a little bit about what you were trying to do here?
So what it boils down to is it saves each time the opponent cooperates and defects. And the first thing it does is checks if the last 2 statements that the opponent gave were, whether they were the same or false. If they were the same, then return that. If they were false, move to how many times they cooperated and defected. If they cooperate more times, then return cooperate. If they defect more times, return defect. And then after that, it moved to random.
So what it was several ifs in. What did it finally get it to random? If T equals F. I see. At that point, you flip a coin. So it's random sometimes, but not terribly often. All right, and we'll maybe look at a couple more. So we'll glance at Morgan's random. You're the first person to have 2 show up in the top tier.
That's granted. This may be because I tried to test them, but it's kind of hard to test your own against when you don't have that many good examples to actually test. But yeah, okay. So this one is a bit of a. This was the one where I used the array. The idea was that the array, it would call a. It will call for a random. It's kind of a combination of tit for tat and basically if a certain number is called through this random num thing, it'll if it's a 1, it'll detect false. It'll automatically just turn it to false. If it's
So it cooperates.
If it's a 10, I think I meant to put true here, but I think I meant to put true here, but it'll.
Yeah.
But it's the idea. The idea still stands. Then else it'll just run tit for tat.
Okay. So it 20% of the time always cooperates, and the other 80% of the time it runs tit for tat. So it's like an occasionally friendly tit for tat, but
Yeah, which actually I would make a note of 3, but whatever.
all right. And then Elijah, why don't you talk about your top strategy? It also looks a little complicated.
This one, I was trying to count the times it defected, and if it defected more times, then I wanted it to, I believe, also defect, and if it counted it less times, I wanted it to return, to not defect.
Okay. So here's an interesting question for you all. Did anybody try to implement strategies that were designed to be exploited by your top strategy?
What do you mean?
So every now and then in this class, people have come up with things where a strategy will automatically cooperate all the time if it recognizes something you've done. Yeah, Tate.
I did. So the strategy beat it though. It's on a 4 only starts behaving tit for tat if you defect twice in a row.
Right.
And I have another strategy that probes with like defect, don't defect, don't defect, don't.
And so it was supposed to exploit Tate Zellner 4.
Yeah, and then it looks in the past, and if it's responding to the defect,
Yeah.
it stops and it splits tit for tat.
Okay. So which one is the exploiter?
I think it's probably 5.
Okay. So let's glance
I
at
did
that.
not- honestly, I did not think of that, but because I do have a variation with that.
I see. Yeah. So Tate Zellner 5 has this pattern and then tries to detect and exploit the other one, but it turned out the other one did better than it.
But I think it's because all the other good strategies were never forgive. And if you don't forgive this strategy, it sucks.
Right. Yeah. Very, very interesting. Yeah. So yeah, this always pops up, and it's interesting to see its impact. All right. So it says something interesting. I'm not quite sure what. That in this family of strategies, forgiveness is punished.
I did not expect the site to get as high as it did. My site, I expected one of my other ones to, but not.
Yeah. So, all right, cool. Any questions on tit for tat? Cool. It looks like you all had a lot of fun with this. I definitely had fun looking at it. I should have these graded for you before lab tomorrow. All right, let's move on to today's topic. So we've talked a lot about arrays up till now. What I want to do today is look at them from a different point of view. And what motivates this different point of view is thinking about different kinds of systems the array might be thought of as representing. And one of the most common and important such systems is the idea of representing a grid. So, what do I mean by this exactly? Let's imagine something like the following. So you've got a 4x4 grid. And why don't we go ahead and label the axes as well while we're at it. So we might call this row 0, row 1, row 2, and row 3. And that's column 0, 1, 2, and 3. So looking this over, here's an interesting challenge. How might we represent this data structure using a one-dimensional array? And the reason it's important to think about it this way is that, as we've discussed many times now, deep down, one-dimensional arrays is all there really is, and everything else we do is just building on top of that. So, what do you all think? How can we represent this using a one-dimensional array? Thoughts? Yeah, Elijah.
I mean, I guess you could have like the first, have integers count, and then the first part of the array be like 0, 0, and then whatever you want to put, and then 1, 0, and then 0, 1.
Okay, let me see if I'm understanding you correctly. Okay. So how many total elements do I have in that grid? All right, so let's see if I can draw a 16-element one-dimensional array. It may be a challenge, but let's see. I think I can. There we go. That should be 16 elements. So Elijah, what would be the coordinate that the first element corresponds to? Okay. And then what about the next one? Mm-hmm. Okay. Mm-hmm. 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 Mm-hmm.
3, 1. 3, 2. And then 1, 3. And 3, 3.
Okay, so starts here, then goes there, and there, then goes over here, and then up there, there, diagonally over to here, then over to here, then up here, 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 there, there, there. We go back here, and then there. So let's talk about pros and cons of this particular labeling. I want to begin with the pros. It mostly works. It winds up that we duplicated 1, 3, and we left off 0, 2, but a minor imperfection. I think the initial origin of it is what you might think of as a diagonalized spiral. That is, you kind of go here, then here, then here, then here, then here, then here, then here. It sort of turned into something else before we got there, but we can certainly grasp what the vision was, And if we were to get to that vision, in a way, what's nice about it is that it's an ordering of the relationships. Again, this didn't quite get there, but ultimately in terms of the sums of the coordinates, right? So you have 0, then you have 1, then you've got forms of 2, 2, 0, 1, 1, 0, 2. Then you've got sums of 3, sums of 4, and so forth. So that's valid, it's a way to think about it. A probable con is complexity of implementation. Complexity of implementation. How precisely to create that is probably not altogether clear. Nevertheless, it's a successful assignment as far as it goes. In spite of that success, I am going to have to destroy it. And inspired by what worked well and gaining ideas from maybe what didn't work quite so well, what might be some other ways to set up this relationship between these pairings? Thoughts? Yeah, Tate.
We could divide the array index by the number of items in a row.
Okay.
And then the actual result of the division would be the row you're on, and the remainder would be the column.
Okay, so let's work with this idea. So what Tate is suggesting is you can take an index in the big array. If you perform an integer division, it can tell you your row. And if you perform a modulo, it can tell you your column. Let's try the idea out. At element 0, we have 0 divided by the width, which is 0, and 0 mod the width, which is 0. For element 0, it works perfectly. All right, so element 1. 1 divided by 4 is 0. So we're in row 0. And 1 mod 4 is 1. We're in column 1. So that's, whoops, 1, 0. Okay. Now at 2, we're at 2, 0, and 3 comma 0. Now element 4, 4 divided by 4 is going to be 1, and 4 mod 4 is going to be 0. And 5 divided by 4 is going to be 1. 5 mod 4 is 1. 6 divided by 4 is 1. 6 mod 4 is 2. And you know, I think we're starting to see a pattern. Well, you know, that really could work, right? So you've, in terms of expressing the index in the one-dimensional array, we have 0, 0 is 0, 1, 0 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Wow. So that's pretty nice. And what's nice about it is Tate stated the rule in terms of converting the one-dimensional index to 2 dimensions, which is important. We wind up needing to do this. But the rule also works. It's also readily invertible, right? So in other words, I can take the row I'm in, multiply it by the width, and then add the column, right? So let's make that as clear as possible. We can take the row, whoops, multiply it by the width, and add the column. If you prefer, you could think of it as y times width plus x. You might be wondering, does it have to be in that order? And the answer is no, right? You could also do x times the height plus the row. And that would be the inverse of this in terms of the mapping. But it would certainly work, right? So there's no particular approach that's intrinsically superior. I think we might have a tendency to prefer this approach simply because we are accustomed to reading in rows from left to right. And so I think the visualization becomes more natural for native speakers of English, right? Where you start at the left, you go all the way across, and you wrap around. You start at the left, you go all the way across, and so forth. Just because that's how our writing system is laid out. In that sense, this might feel more natural, but I hasten to emphasize there is nothing intrinsically superior about this compared to that scheme. In different programming languages, both schemes are used for aficionados of the history of this sort of thing. The C programming language used this approach, which is called row major, and the Fortran programming language used this approach called column major. But again, it doesn't really matter. Here's what does really matter. How much overhead is involved in these calculations in comparison to the overhead for indexing on a conventional one-dimensional array? So how much extra work? Yeah. How much extra work are we talking about compared to indexing in a standard flat one-dimensional array? Let me put it this way. Is it a lot of extra work or maybe a little? A little for a computer. A little for a computer. All right. So I actually agree with you, Elijah. It is a little for a computer, but let's dig into this a little deeper. Does this extra work prove to be proportionate to the number of elements in the grid? In what way?
We have to multiply and add each one, so each, so depending on the number of items in your grid, it would be the number of operations.
Let me rephrase it maybe. Let's say I have 1,000 by 1,000 grid, and I want to do a lookup at 750, 500. Does doing the lookup at 750, 500 require me to do operations on any other elements in the array? It really doesn't, right? It's on top of a regular array, we have to do a multiplication and an addition. And it doesn't matter how big the 2D grid gets. So in that sense, it's just a little more work, but it's not especially burdensome. That's good. We don't want it to be burdensome. So this is a really nice solution to coming up with a way of turning a one-dimensional array into a two-dimensional array. Now, some people would nevertheless complain that this arrangement has a curious disadvantage. And I'm not going to pretend for a second that this disadvantage is obvious. Here's the idea. It is also imaginable that in a two-dimensional array, that you might want rows of different widths, right? So it's imaginable that each of these, this one might have 5 columns and this one might have 3, for example. Now, if you wanted to do this, can you imagine a way of accommodating it in this framework? What would it take to accommodate it in this framework? What knowledge might you need? I mean, in the general case, you can't really accommodate it unless you know the maximum width you would ever use. If you do know that, you could accommodate it by leaving some of the cells blank, basically. But if you don't know that ahead of time, then you can't really accommodate it. So here is a different implementation strategy. And the nature of the strategy is already given with how I've been drawing things. This other strategy is to have an array of arrays. In other words, you have an outer array, each of whose elements is an array. And then you've got your inner array, which contains the actual values. So this, of course, brings up an important question, which is, what does Java do? And the answer is that Java, does this. It does an array of arrays, for better or worse. And there's another issue. If that's what Java does, deep down, what is my own personal preference? deep down, my own personal preference is actually this. And the reason I would say that is if I'm going to have a fixed size array, I might as well just fix it in both dimensions. It turns out that this approach winds up having some extra overhead because it turns out memory lookups wind up being expensive operations. I'm going to talk about that in more detail later in the semester. But the reality is, anytime the CPU has to load a value from memory, it takes a lot more time to do that than for the CPU to do an arithmetic calculation. Because I'll go over some reasons for that later in the term. But that's kind of the way that it works out. And the other arrangement winds up running a bit better in practice as a result of this. That said, this does offer some interesting flexibility, which is not something I would completely disregard. So, having said that, something that's really nice about Java is that it doesn't exactly stop us from doing either approach, right? I can always create a class which is a fixed size grid, and I can build it on top of a one-dimensional array. So what would that look like? Funny you asked. So let's go ahead and create a new project. A new Java project. Next. I will call this grid. I will put it, and okay. Come here. My ability to hit the arrow is limited at times. I'm sure none of you have experienced that. So I'm going to create a new Java class, and I will name this class grid. And so I might have something like this: private int grid, and then for my constructor, what might I need to tell the constructor about my grid? Thoughts? What might it need to know? Number of rows and columns. So we'll say it needs the width and the height. And so to create my array, it's going to have a number of elements equal to the width times the height. But I'm also going to need to keep track of those values. So then I could imagine having a couple of methods here, something like public int get, given an x and a y coordinate. I can return grid bracket x times the width plus y. So if I've got something like x, or no, I have this backwards, don't I? It's y times the width plus x. Yeah. If I were to have y times something, or x times something, it would be x times the height. And then I could have something like set and I would say grid of y times width plus x is equal to some value. And now I've got some basic simple stuff in place. So I think I am ready to create a test. And I'll go ahead and use JUnit 5 for that, and I'll add it to my module. And then I'll create a simple test method. I'm going to call it test1 for now, unless I eventually come up with something smarter. So here's some basic things I might test. I might create a grid G equals new grid, and I'll make it a 5 by 3. And then I'll set at, say, 3, 1. I'm going to put a 10. And then I'm going to assert true or assert equals 10, comma, G dot get 3, 1. So this is kind of a simple basic test of, can I put things in and get things out of my grid? And it turns out it works. It works very nicely. There's nothing terribly difficult about it. So what a relief. So that is the basics of a grid, So this isn't all that complicated a data structure, really. It does its job very nicely. In practice, I've wound up needing to create this data structure a number of times over the years. More often than not, it's been in the context of image processing. And the reason this has happened is that when you've got some kind of image acquiring device, namely a camera, right? The way that the device typically works is it does its hardware magic. It takes in light. It has a physical grid that for each square kind of figures out what's the predominant color, reports that color, stores it. And then what it dumps into memory is it takes the entire image and then just dumps it into a single giant consecutive piece of RAM, or in other words, a one-dimensional array. And then to do anything interesting with it, you want to think about it in 2 dimensions, so that you're visualizing it as an image and working with it as an image. And so then, yeah, you typically wind up coding something that looks like this. And it's pretty effective. It's pretty effective. So cool. Any questions about the grid? Okay. So something that I was supposed to talk about last week and forgot about, which means I'm probably going to extend the deadline, is your first project in the class. So, in fact, I so neglected to talk about this that I didn't even set up the hyperlink properly. So I think it is project1. Oh, boy, is that embarrassing. I'm not going to have it due Friday, yeah. Boy, is this awkward. Here we go. View page source. Basically, if you're ever curious about anything that I'm going to be doing in the class, I've got the hyperlink present in the page source. And you can always just look at that. Of course, before I unlink it, I always reserve the right to change it around. So for your first project, I want you to create a useful program in Java, which can really be anything you want. You do have to complete it independently. Instead of use Eclipse in Java, you can use IntelliJ in Java. There should be input and output in a main class. You have to use an array or an array list somewhere in the program. And I'm going to go over array list in a moment. You should have at least one class besides this main class, which contains the main that launches everything. Okay? And it should do something useful, interesting, or fun. It need not be complex, but it should be something that someone would conceivably want to use. Conceivably want to use. And you can use anything in the Java API that you want, any library you want. You're not limited to stuff we've covered. So if you learn about something interesting, you're free to use it. So here are a few ideas. You could do a simple text game, and an example of such a game is NIM, where you're given piles of things and you get to eliminate certain numbers of piles, and you take turns until somebody's left holding the bag. You could replicate the water jug game from Computer Science 150, the Die Hard 3 experience. Something like Tic-Tac-Toe or Connect 4, Game of Life, what have you. But basically something that lends itself to a straightforward textual interface is what I'm looking for this assignment. I realize speaking with you right now, I haven't talked about how to do text input. I will throw together a short video on that for you and post it. It's not terribly hard, but it does take a little bit of effort to think about. But with the few minutes remaining, I do want to talk about array list. Array list is the equivalent of a list in Python. It's not quite as flexible. It doesn't have the slicing bit, but it's a resizable array. And it's what we all tend to use in practice rather than flat fixed-sized arrays. Let me demonstrate a little bit about how we tend to use array lists as a practical matter. So, here is a quick array list demo. I'm going to create an array list, and the angle brackets indicate the data type within the array list. And it's red, so I Alt-Enter, and now it's imported. Now it's available. You know what it looks like? I am going to do input real quick. So I'll show you how to set up input right now. So you create a scanner. And the scanner wraps around system.in. Oops. And then you say something like, while the scanner has next, strings.add s.next. And then when we're done, we can do something like this. Less than strings.size. And then for each of these elements, we can print out s.get, no, not strings.get. Whoops. So let me go ahead and run this for you all. So this is a test. And then Control D. So see this hat D? I held down the Control key and I pushed D, and that signals I'm done entering input. And so that caused has next to be false for the scanner. And then it printed everything out. So that's a straightforward way to get some text input, actually. So I don't need to do a bonus video. It'll just be part of this video. Aspects of array lists. Get is how you look something up. There's also set. Set turns out to be not quite as useful as add. Add just sticks something on the end of the array list. The way they tend to be used in practice is you just sort of add a bunch of things to the end and then look at them. That said, there is the set method as well if you want to change something that's already added. The reason add is more common is the fact that the array list has no elements until they are added. So when you create an array list, it always is empty when you create it. And then you have to add things to it for it to have any contents whatsoever. So array list is extraordinarily useful. You're going to see it all the time and use it frequently. So I'm going to have the project be due on Wednesday of next week. Project 1 will be due Wednesday of next week. I will update the web page and Moodle to that effect as well. This will be due Wednesday night of next week. All right. Oops, ran over. Sorry about that. I'll see you tomorrow in lab.